Gotten the go-ahead. Hey, everyone. Presentation about simplifying distributed systems with Apache Kafka. So just to get a good idea, how many people work with distributed systems right now? Few. Some people still got the monolith. Maybe some people just got the database and something else in the web front end. How many people have any knowledge or experience with Kafka, Apache Kafka? Not much? All right, great. It means it should be very informative. All right. So, my name's John Holland. I've been doing this software thing for 10 plus years. You lose track of that number after a while. For the last couple of years, I've been working on a large microservice architecture and using Kafka as part of that. Many other things involved there, but focus on those pieces right now. So I've been doing a lot of distributed systems work, probably for like about the last 5 years, and things have changed quite a bit. It feels like just recently, the last few years at least, with some of the new technologies. And I've been at OPI for 8+ years, and the chief technologist of real-time data. So, and real-time data is essentially like big data, except you don't have to wait for it. So that's the new thing, right? Streams. And then Kafka and streams, they go together quite well. All right, so rolling into things. Some of you said you had systems that were distributed. A good question is, why would we distribute our systems? Because for the most part, they're really complicated, and they really got a lot of hard problems to deal with when you do this. So when you initially start out, you're a startup, or you got like a new concept or something. And usually you get the standard issue model of, I got this web server sitting out here, and maybe it has a REST API, or maybe it's doing server-side rendering. And I got my database back here, and this is great. I mean, I got my 15 customers, and they're happy. This thing's stateless, this web server, I don't have to worry about having lots of those. Nice ACID compliance, data's always consistent, no worries. Can't scale it, don't care, I only got 15 customers. If it fails, if it dies, well, I'll have to go get the backup, right? I might lose some data there, but I'll go get the backup, and I'll explain it to my marketing department. So we were really happy with that monolith until we got popular, or other parts of the company wanted to use our great service. So we had to start scaling things. And then their database died one day, and they said, no, we can't have an outage for 2 hours while you reconstitute the backups back into the database. So you have to be highly available. That's your job. So the first thing we do is like, okay, we're nailing this database, and it's our choke point right now. Let's put cache in there. So now we got cache. That's great. We got lots of front-end web services running up there, doing in the stateless nature, doing the requests, hitting the cache. Things are nice and fast. Customers are really happy. We decided to do some database replication, whatever our particular brand of database supports. And so now we have failover. We got a nice cold failover there. So instead of the 2 hours to reconstitute the backup, now we can fail over in 5-10 minutes. We still have an issue because this thing the database still doesn't scale very well. It's still a choke point. So that's a problem. And we've introduced a new problem here too, because now we're updating caches, and we're updating databases, and sometimes these things don't always both happen. So our cache gets out of date, and our database has the newer data, but we don't know if the cache is up to date or not. Most of the time we're good with it. If there's issues, we'll expire out the old stuff and go fetch from the database. Maybe we've worked around it that way, right? Every hour, I'll just go get whatever's in the database in case like I failed to update it one time. So we now have high availability, and we have scaled out a little bit with some issues, but we're working with them. We got workarounds on it. All right, so things keep moving along. Other partners or businesses or even other parts of the company wants to integrate with us. So first thing that happens is they say we had a REST API. They bring out their services and they say we're going to use your APIs to get our data. Now maybe you need to use their APIs to get some data from them. The first thing that happens is now you all are coupled by APIs. So unless you're managing those really well, next time someone changes their API, you're gonna have to go through and make sure nothing breaks. Another thing that might happen here is you might have to do some sort of distributed transaction to make sure that things are consistent across the systems. And we know how distributed transactions go. They don't. They're slow and they have a high potential of having problems. And we have the partial success scenarios still present. So what do you do with out of your 3 calls, one of them fails? How do we do that? Can we go make all the calls again? Do we fail the whole thing? Do we put the failure someplace else and keep retrying a third and just deal with the inconsistencies while they exist? And then we got this guy over here, and he's causing us trouble. He's decided, I don't do the API thing really. I like databases, so I'm just going to go and query your tables to get my data. And yeah, we know how that goes. So you might have situations like this popping up where they're going through the back door of the database and grabbing the data, maybe even updating data. Which if schema changes again, big problem. So that shouldn't happen, but And as things become better, as things keep going and things keep growing, and you put more features in, and people find that your service is useful for a lot of different things, and it's really great in a lot of ways. You get a Gordian knot. You got all these things communicating with each other, and you don't know which way they're going or who's communicating to who very well. Maybe you have some other system to manage dependencies via API. I don't know, but you end up in a place where you don't know who's talking to who and what language they're speaking. So it becomes very difficult to understand and trace through the system. And every time you add something new to it, it gets worse and worse and worse and keeps compounding. Now you may have chosen not to evolve. You didn't evolve it into the situation. You actually chose this situation, and those are microservices. And you choose microservices, you need to figure out a way not to end up there instantly. So that's important if you're going to go towards microservices, which is a very becoming more of a popular architecture, and it does have a lot of benefits. You just got to manage it carefully. So what do we do about all this? All these problems we have. We have all this point-to-point communication. One thing goes down, it affects 6 other things because they were doing point-to-point communication. Network partitions, same issue. We got these multi-dispatch updates happening. We got consistency issues because of that. We have strange failure scenarios that are hard to recover from. We have distributed transactions we want maybe. Maybe we want something highly consistent somewhere in the system. Or maybe we just need to get rid of them because we understand that distributed transactions are probably not in our best interest. We have people integrating in ways that don't make sense, like through the database. We need to stop that. We need to give them a way to get that data without accessing our database. And then you're dealing with your API coupling, which will be happening on all the point-to-point communications. And what happens when you have API coupling is your system becomes rigid and fragile. You can no longer be inventive and creative as you want to be, and you can't innovate because you're stuck in this API-coupled rigid system that forces you either to rewrite entire pieces of things or keep on reintegrating with different APIs. If anytime anyone has questions or anything, you know, raise your hand, yell out. If you're gonna throw something, make sure it's soft. All right, so Apache Kafka. Apache Kafka's genesis was at LinkedIn several years ago. So I don't know the exact date, but it's been a while. Maybe 2010, 2011. In 2012, it became a Apache top-level project. And it started out very fun, very rudimentary. I think it was like 0.7, and it was basically one node, no replication. You dump data in, you get data out, pub sub style. But now, if you go check out the Wikipedia page or something, they're going to say, look at all these notable companies. And you're going to see a bunch of names that you use every day, besides LinkedIn. You'll go there and you'll see the, it's like Microsoft and Twitter, and you go on and on about who uses it right now. And Kafka is modeled as a distributed transaction log. So most people understand logs. It's just, big string of data that keeps going on and on and on. And that's how it's modeled. All right, let's get back into a log. All right, so in Kafka, all the data is stored in these append-only logs. They're immutable, and you see these immutable append-only logs commonly used in databases. If you go to Wikipedia and you look up MBCC, which is multi-version concurrency control, I believe, you're going to see that basically every database you can think of uses this model to do transactions and to handle failures. Fun thing about these logs is they're ordered. So if you consume from a log, it's always going to be in the same order by time. So as you go from the earliest time, the tail of the log, to the most recent time, the head of the log, every time you consume that log, it's always going to be the same. And everyone's going to see it exactly the same. So you can look at it as being very consistent across the entire system. And when you take this and you consider how streaming is the new big data processing model, the log fits right into the stream. You can essentially look at this. This is on disk, or you can look at going across the wire as a stream. All right, so let's dig into some of the details here about Kafka. This is how the data is structured and stored. So in Kafka, you have a concept of topics. And every topic is configured with a certain number of partitions. You can have from 1 to any number you want. Sky's the limit. There's probably some constraints you should consider, but so what you have is you have the topic, and then you have your partitions. Each partition is assigned a number. So you'll have partition 1, 2, 3, and 4, and each partition will have a log. I didn't detail it out here, but the logs will also have segments. If you look at Kafka and you read up on it, you'll see that topic is more of a concept for us. It really deals with partitions. It does all its work at the partition level. So when you want to replicate data, you're actually replicating the partitions. And you can take these partitions and you can put them across your entire cluster in any way you want. Any broker can handle any partitions. You probably want to balance it out. You don't want to put like 90% one broker and 10% in the other. And the partitions are important when it comes to scalability. And we can talk about a little bit when I get to consumers. But essentially, it limits the parallelism of how the data can be consumed by the partition count. So in Kafka, you can run it with as a cluster. Now you can have small clusters. You can have a single node cluster if you want, just a single broker, or you can have a cluster of 50 if you'd like. I generally speaking, I don't hear a lot of good stories about very large clusters. You probably don't want to exceed like a dozen or something for the most part. But a model that some people, I have heard some larger clusters at bigger companies, but a lot of times what people do is instead of having clusters that are huge, they'll actually just have more clusters, and then they'll do data replication between them. But we have our friend Zookeeper in here, and if you know anything about Hadoop or MapReduce, you've probably recognized that name. Zookeeper is a coordination service. It does things like leader election, strongly consistent. Also keeps configuration that you can use for locking and coordination between other parts of the system. So it uses Zookeeper primarily for leader election, also for the configuration piece. The leader election part is each broker here, we have 3 of them. Each one is going to be assigned partitions. And there may be replication of those partitions also assigned to other brokers. The leader election tells us of all the partitions across all the brokers, who's in charge of that partition for that topic. And that will be the one that actually accepts writes. So that one used for Zookeeper there. There's also the brokers themselves have a concept of a controller who's kind of in charge of initiating cluster-wide activities, and they use Zookeeper for that also. There may be other things I haven't seen or found that uses it for, but those are the 2 that I am most familiar with. If you have used Kafka or you read something about an older post about Kafka, you'll also see that they talk about how the consumers use Zookeeper for coordination. That's no longer true since .9. So that is for versions prior to .9, which is great because the less Zookeeper you have, the better off you are. And inside Zookeeper, it keeps configuration for the broker in general, and also the topics and the consumers. So a lot of times the consumers will have their group IDs in there, and the topics, there's several parameters you can set on the topics themselves. The partitions are actually segmented out. So you see we have partition 1 there, and via the configuration of the topics, you can decide how big the partitions will get before it rolls into a new segment of a partition. And this is how you control retention, and there's some other odd things that you can do with it. But for the most part, with the configuration, you can set how often it rolls new segments and when the segments expire. So if the segments are smaller, you'll get more fine-grained expiration. Bigger ones will sit around longer. So if you have big segments of, let's say, like a gigabyte, it's not going to expire it out based on your retention policy until the most recent message in that thing expires. So the last write time. But if you make them smaller, you make them 100 megabytes, then it will expire out faster and you'll reclaim your disk quicker. So there's trade-offs there. There's trade-offs everywhere. Let me see, going back to the segments. Right. So the other thing too about Kafka is it was originally written back in 2010 or whatever to work on commodity hardware, which is different than what we consider commodity hardware now. Most people are probably actually running in some sort of virtualization. So, but it was written to take advantage of spinning disk. Everything is read in sequence across the segments and the partitions. So it never has to do, it doesn't have to do a lot of random seeks. So it makes it very quick access. The other part is it uses the operating system's file page cache to do most of its reads and copies through memory straight to the sockets. So a lot of times data will come in and it'll go straight to the socket, never hitting the file system until the flush occurs. So you can get very high throughput that way. I talked about a little bit about this already, but this is shows how the replication kind of maps out. So we got our this is replication factor 2 here. We got 3 brokers. Our first replication is the primary partitions. Then you see the replication of the partitions across going to different brokers. So this allows you to do failover. If the leader dies for whatever reason, goes out of commission, then the replicants will take over, and you'll still be up. All right, let's talk about consumers. All right, so consumers are grouped. So you can think of an application, the reporting application or the entity application or something. You give it a group. Now there may be many consumers inside the application. So let's say you have your reporting application and you have 4 instances of it running. You'll have a consumer group of 4 consumers, and they'll coordinate with each other across the partitions. So they're all reading separate data. And what this does is it means you can scale the number of consumers you have per topic and per consumer group up to a point. If you exceed the number of partitions, they will go idle, the consumers. So if you have 3 partitions, having 3 consumers in a group, that will assign all the partitions across. If you add a 4th, so sorry. If you have 2 here, it'll assign partitions accordingly. So one will get 2 and one will get 1. Now, what happens when a consumer stalls or dies or goes bad for whatever reason, or you're rolling in an update, right? This will cause what they call a reassignment change on the consumer side. So, and this happens whenever a consumer comes in or a consumer leaves or a partition count changes. What happens is they go back through leader election across all of the partitions again, and each consumer will be reassigned. It happens pretty quick. It can cause some message duplicates depending on where they are when it happens, but otherwise it happens quite quickly, and you probably won't even notice it. So just some pictures to better illustrate it. Here we are. We got 1 consumer, 3 partitions. All the partitions going to 1 consumer. Same 3. We got 2 consumer. 1 consumer gets 2. 1 consumer gets 1. Here we got equally spread. And here we have more consumers than partitions, and this guy doesn't get anything. And then we have the failover here. So we got everyone happily consuming. Shiny brand new guy gets spun in, and we're good again. And that'll all happen automatically. Not the whole spinning a new one in, unless you got some sort of auto scaling or something happening there, something to catch it. but it'll be completely seamless. And most of the time, you don't even know what happens. So, for example, when you're rolling out new versions, you can kill one, bring a new one in, kill one, bring a new one in, kill one, bring a new one in. Just, you know, typical rolling deploy. You can also do fun things like do kind of like a canary model where you kill one and you bring a new one in and you just let it soak up that data for the one partition and see how it does. So it gives you lots of options on how to make that deployment happen and different ways of ensuring that it actually works. Okay, another interesting point. Data is never consumed. If you think about classical pub sub brokers, a lot of times there's data comes in and somehow it gets routed to a bunch of different consumers and they get a queue. Each consumer has a queue, and as they consume that data, they destroy it. So the queue empties out. You get 0 in the queue. In Kafka, that's not the case. Kafka will retain all the data it receives until the retention policy set on that topic tells it to get rid of it. And those retention policies can be either by size or by time or by both. And there's a special one called compacted, which I'll talk about in a moment here. So what that offers you is essentially a way to go back in time if you want. So if you do have problems, you can go back and fix them and then get the data back out with the fix. But the consumer groups track by offset. So in this example here, we have this log and we got all the offsets in here. So we have offset 1, 2, 3, and n+1, so on and so on. And the group has an offset 2. It consumes some data, it does a commit back, and now it has an offset n. Now if it dies and comes back, because it did the commit, it'll start at offset n+1. And that's how it tracks. None of the data is actually lost, or destroyed, or consumed. It's still there. Everything is just basically pointers to offsets. And we have the producers. So we talked about the consumers, talked about the brokers, mentioned Zookeeper, and we have the producers. So the producers, you can use them to produce 2 types of messages, keyed and unkeyed messages. The keyed ones are really interesting. The unkeyed ones are really good for throughput. Essentially, with unkeyed messages, they're gonna supposedly round robin across the partitions. This would be per producer. So if you have lots of producers, they're gonna have a different round robin sequence they're gonna use. Now, if they're keyed, they're going to be hashed and put to the same partition based on key every time. So if you have these keys here, ABC, XYZ, 1, 2, 3, every ABC key is always going to the top partition. Every XYZ key is always going to the second partition. The 1, 2, 3 and OPI key, they go to the last partition. And they'll always go to those partitions with the caveat of, unless you increase your partition count, then everything's blown out of the water for a while. So take it seriously if you need to increase your partition count and you're depending on ordering, because it will break it. Now the producers, they can be configured for different delivery guarantees. So if you really just need throughput, you don't care about whether you get all the data or not, maybe these are like click streams or something, you can do act0, and the moment the producer sees it, drops in his queue, it says, I'm good. You can go do the next one. It'll batch it up, and then it'll send it off later. Act all, this means that if you have partitions that are replicated, it's going to ask that all the replicant brokers also acknowledge that it received it. So now you have copies across the whole cluster. And they'll take the longest, but it's the most durable. And then ACK-N, you can pick. Like, I want 1 ACK back from a replicant, or 2 or 3 or 4, whatever. The producer attempts to be very performant by doing batching as much as it can. So it will try to hold the messages in memory until it's forced to do a flush. And you can either choose to, there's some settings on there that you can play with to decide how long it'll keep it in memory. That'll increase the latency, but it'll also probably increase the throughput. So you got your trade-offs and how big that queue can be. So with all these things, there's 25 different configurations depending on your needs. Any questions? All right. So log compaction. I told you there was a special policy for retention that didn't actually expire the data, and that's called log compaction. It's based on keyed messages, and it's really interesting because it'll always retain the last message for a key, and you can actually use this as a data store if you want. So you can think of it as kind of like updating a row in a table, right? Every time you send that key in again, it'll update that row. You can delete them also by sending in empty payload. If it sees an empty payload for that key, it'll just wipe it out. This is really good if you need to do like a really quick data store that maybe doesn't have a lot of data in it, and you just want to store a bunch of random stuff in there. Don't care about schemas or anything. Don't want to spin up a new database. You can just set up a log compacted topic of one partition for this particular thing, and you're ready to go. And then it's really just a bunch of event-driven stuff happening in your app, and I think it simplifies things. Then you're really just working with events at that point, and whatever data you choose to serialize. Here's a depiction of it. So we have our logs here, and we have that in there. The red smears on the letters are supposed to indicate that they're going to be compacted away, and the green ones are the ones that will remain. So the compaction occurs, and we have just the green ones left, and those would be the most recent. And I'm sorry, I think I got reversed, because yeah, that should be oldest, and that should be most recent. Over here on the deletes, so the special thing about deletes is that when the delete occurs, it'll actually stay in the log for a while. And the reason is that consumers can come and go, and they may leave for a while. So let's say you have a consumer, and it's receiving this compacted log, and it has a problem, and it's gone for a day. Then it comes back. If you're deleting out those deletes before it comes back, then of course it will still retain that data. So you need to keep those around so we can catch up and get an accurate set of data. All right, let's go back to our distributed system. So probably the biggest problem we had is we just got a lot of systems talking to each other, a lot of crosstalk, right? We're not sure who's talking to who and what API versions they may be using. Things grew organically, or we went microservices without thinking through how we're going to organize this. So with Kafka, what you can do is you have everything, you treat it as a central hub. Instead of all the point-to-point communications, you depend on just the data being available to the other systems as needed. So we got the producers, we got the consumers, and vice versa. You pick a number of topics you need. Maybe there's a topic for each kind of data going in. That's usually how wired together. So you have orders in one topic, you have users in another topic, you have customers in another topic, you have the click stream in something else, and you have the inventory log in another one. And instead of them talking to each other, they just talk to Kafka. And you depending on the number of partitions, you can scale each one of these things up individually as needed. So maybe something does a lot of processing, and it needs to have more instances to do that processing with. Maybe something is just really a pass-through, and it doesn't need more than a couple. Since you have all this data available, we can add new services easily, and it can choose whatever data it wants and start using it right away. It doesn't have to depend on any API calls. It doesn't have to depend on a database or cache, because it can make its own. If it's taking in the order object and it's taking in the user object or the customer, and really it's creating a user order, then it can create its own database that is refined and efficient for what it needs to do. Maybe throw a cache in there too if it needs to be faster. And it'll be completely to itself. It can handle schema migrations on its own. It can handle all those details without any other interaction from any of the other services. Because really, all we do most of the time in these systems is we trade data. Quick depiction of what it might look like. So here we have 3 services, one coordinating with the 2 others there. We do an update. Fails. Okay, now we have one system out of step with the other. How do we fix that? Well, we're gonna have to do some monitoring or logging or something. We're gonna have to have something else to go in there and fix it. Because if we don't, we're permanently inconsistent, which means we can't depend on getting the same results from these different systems. So let's take that and look at what happens when you throw Kafka in the middle. Now, of course, this could be used, another broker could probably fall in here too. Now I'll talk a little bit about why those other brokers don't always, or aren't always suitable. The event goes in, event A goes to the other 2 systems. They can fail as many times as they want. You don't care. This one completely isolated from that one. Eventually, that data should be consumed and it'll be consistent. So another thing that happens is you have your large system. It's got all kinds of moving pieces. You draw your boxes around chunks of it and say these are subsystems. We got our domain boundaries and so forth. What you can do is, I was talking about it, having several clusters or having one big cluster. Here's a model of several clusters in it. What's nice about this is now they're isolated. Now, if the cluster has a problem, Kafka's not perfect. Sometimes it has problems. It doesn't affect the other guys. They can keep humming along. And for example, here, this is something I made up. Storefront, taking in data, maybe new users, new orders, new comments, whatever. And creating data, putting it into their Kafka cluster, and these other systems subscribing to it. So we have ordering, taking orders in. We have the customer management taking the user stuff in. We got data analytics taking everything in. And they're completely separate. So data analytics could get hosed up for a while, and oh well, I'll come back a day later and they can catch up. But it doesn't affect our ordering or customer management at all. Let's say we want to bring in a 4th system. Let's say we want to do inventory, and we want to tie it in there. Let's say inventory is related to ordering. You could tie inventory off of ordering if you wanted to. Right now, there's nothing else you have to worry about. No interdependencies between APIs and so forth. No inconsistencies. You just do it. So any questions on that? So there is tooling to do this type of work already available off the Kafka project. And it's called Mirror Maker. You can use that, or you can also do like your off by one. You can create it yourself. There's also another tool called Kafka Connect, which might be able to do some of this for you too. So there's different ways to achieve this. Let me see. Let's go to data center replication. So let's back to that failover, right? So okay, we got hurricane season. We got everything on the East Coast. Bad idea. So we decided we're going to do another data center. This one's going to be in the middle of the country. No more hurricanes, right? we need to replicate that data. So depending on however you do your data center replication or how you use your data centers, you may have a hot, cold, or you may have two active in those. You can also use Kafka to do this across the WAN, using basically the same tooling I was talking about before. Mirror Maker, Kafka Connect, your own solution. I think Uber has something too. But essentially it's consumers and the producer tied together, and they just replicate data back and forth. Just watch out for cycles. And if you want to learn more about that online, there's some good stuff by, I think it's Todd Paulino, a LinkedIn guy, and he talks about what they did at LinkedIn, and it's very educational, interesting. All right, so now we're going to talk about streams, stream processing. Everyone likes streams, right? That's what we're all going to be playing with someday. So a lot of times you'll find that the services you're building that have a lot of these connections occurring between them are really just stream processors hiding behind APIs and point-to-point communications. For example, here we got this A event going into this facade service, Mr. Pink, and it delegates to Mr. Green and Mr. Blue, and they come back and it goes and it aggregates it back to Mr. White over there. So you know, A comes in, ABC comes out. What you could do instead is we just have Mr. Pink here, and he actually takes in all the streams A, B, and C. He creates this aggregation, and he calls it ABC, and now Mr. White doesn't just collects ABC as they're produced. Stays up to date, doesn't have to worry about making calls through. I don't know what Mr. Pink does. Maybe he does transforms the data, maybe he does enrichment of the data, maybe he applies some business logic to the data. We can also do analytics and stuff with stream processing. You've probably heard of some of the bigger frameworks out there. The bigger frameworks out there: Storm, Spark, Flink, Nefi. But there's also one called Streams, which is fairly new with .10. And all those other frameworks, one thing that really gets you is you have to deploy the world in order to make them work, and the world usually includes Yarn and Zookeepers and HDFS file system and so on and so on. So a lot of moving pieces. Kafka Streams is a little simpler. You can deploy it in a Docker container if you want. But it allows you to do analytics and windowing and out-of-order processing and all the really cool stuff. Wrong way. Whoa. All right. So another thing here, data coming in. We got these disparate systems. They're producing data that's really similar, but it's just off by that much, or it's like XML and JSON and fixed width. So we tell them, produce in here. We're gonna have a stream processor down here that's gonna take care of all this data, all these oddball formats from the 80s, 90s, and today. All they are. And we're gonna go into the format we like, format X. Then once we're in format X, the rest of the system can be adhere to our standards there. And that way you can isolate them from all that, instead of having all these different pieces having to deal with all these different formats. Another thing too, this is maybe a little more advanced, especially on that side, is you can stream data out of different data stores. For example, this is done with MySQL. LinkedIn does this with MySQL. There's a couple projects out there on that one. Postgres Bottled Water does this. Cassandra, there's something called Kafka Connect, which has a Cassandra connector, which I think actually just kind of like keeps track of offsets in Cassandra and does polling against it. And and makes it all available via Kafka. Change data capture, right? CDC. And the opposite route, data is coming in, and we're going to populate our stores with it. Up-to-date caches, if you got a Redis or something out there. Dumping everything to HDFS or S3 for analytics. Cassandra again, if you need a time series or some sort of key value store. You can also do it from a file system, simply enough, if you want to use it for log aggregation, like application logs. This is cool stuff, the CDC piece. You dump it into MySQL, and you have something off the back end here. You can get your asset, and then you can make it available to everyone else via Kafka. So it's kind of cool. So I'm talking about streams and caches here. So the compacted log is a lot like a cache, or it's a data store, essentially. And it can be used to say, I was talking about CDC. So you got this entity CDC, so you got your users in your database, your MySQL, and they're changing, and you're creating this change data capture stream out of it. It goes into here. This processor here takes it, creates a compacted log, basically, of it. So creates all the users in some sort of format in this compacted log. And then this other thing puts this data into the cache. So this cache is always up to date, right? And all the data is always in Kafka. The cache blows up. New cache comes in. Spend 4 seconds loading it, depending on how much data is in there, and you're ready to go again. Need more than one cache. Load up 4. Bring in a new database. You need to log all that stuff in. Load it up. Forget about schema migrations. You don't need them anymore. You just have to understand the format of that data in there. Brand new schema. All right, load it up. And the other thing too is if your data is pretty small, if it's very constrained or something, if it's on the scale of like a couple million records, probably just keep it in memory. Don't even have to do caches or databases or anything. Just keep it in memory. Very fast. All right, so I don't know, but sometimes things break. Maybe it's just me, but every once in a while, like 2 in the morning, I wake up and phone's buzzing in my ear and something's broken. What do I do? I fix it. All right, we fix it. A bunch of data got lost somewhere. What do we do now? We replay it, right? Because that data's still there. It's still in Kafka. You just got to change our pointer. So that's what we do. We change our pointer back in time. Take the system, and it broke at this offset. Now in .8, this is tricky because you have to track the offsets in time yourself. But in .10, they actually put a timestamp on this stuff. So it broke at 9 o'clock last night. We're going to bring it back to 9 o'clock and replay everything. System's up to date. Things are consistent. People are getting their shipments. And then any questions? Because now I have basically a list of things to keep in mind if you're going to do this. So distributed systems, Kafka, Zookeeper, anything? No? All right. So some things to keep in mind. Data formats. This is your lifeblood here if you're going to go this route. You're going to find out if you get a lot of data pumping that your bandwidth is your limiting factor. Disk, cheap, big, gets lots of it, no problem. Memory is about the same thing. You can always find new nodes and CPU cycles. But bandwidth is an issue. So the smaller, the better for your data formats. You can either pick a binary format, or you can pick something that compresses the heck out of your JSON. Just know that means more CPU cycles. But and you also can't send your interesting like JPEGs and stuff across it very easily without inflating it. Make sure it's well defined. You don't want to just send anything through. That works great for like the first 2 months. That's awesome. 4 people on your team. Each one has a service. You all sit around the table. We don't need schemas. But then when you have 100 people, 300 services, maybe we should have had schemas. I don't know what data this is. Manage the evolution of that data. So things change. You're going to have to understand forward and backward compatibility. Things should be written so they're forward compatible. They work with old data. They work with new data. They need to be backwards compatible too, so that you're not removing data that's expected downstream. That is also going to be important when you put that data into your Hadoop cluster. You better keep that schema attached to that thing and as part of that data that's stored in Hadoop, or else what is really the use of that data, since you don't know what it looks like. Consumers need to be idempotent. This is important. If you're depending on exactly one guarantee, you will fail. You don't want side effects. So when the consumer receives an order, it shouldn't just create the order without checking if the order already exists or making sure that there's something else preventing it from creating duplicate things. No side effects, right? An order is an order is an order is an order. If you get it twice, it's still one order. So make sure your consumers are idempotent. This is really important for replay too, because when you replay, you may be affecting more than one system, depending on how things are architectured. If you're idempotent, no problem. If you're not, what do we do? Things to keep in mind, messaging guarantees that are offered. You got most once, so that's for data that, high volume data that missing stuff isn't all that critical. At least once, you need the data, you gotta have the data. Exactly once, I gotta have the data, but I can only have it one time. You can achieve this, but it's not easy. And I'll tell you why. You can achieve this from Kafka to your consumer. It requires the consumer to have knowledge of offsets, because you'll store the offset information, that pointer into the log with your data. And then when you start up, you'll go grab the last thing you got and get the offsets so you can start from there. And that will make that exactly once. You will get dupes, even with your exactly once structure here. So you did an ACID commit and you stored your offsets here and you stored your data there. You will get dupes, and it's because you can't control upstream. So upstream might have failure scenarios that causes it to publish more than once. The same thing. So you will get duplicates. That's why it's important to be idempotent. Dead letters and retry. This is an interesting thing. Always talking about, always dealing with it. Basically, I don't think you should skip messages, even if your order doesn't matter. Don't skip them. It makes things complicated, because usually the reason you're skipping messages is because either A, they're bad, so get rid of them. Just log it, get rid of them, find out why they're bad, or fix your service, because it's probably puking on a data format or something and misunderstood, or it's just got a bug. And if all else, then replay the data if something bad happens. Generally speaking, I just retry. After a while, just shut your consumer down, kill your service, whatever. Let some other service, let some other consumer take over, because it might be a network partition that you can't resolve or is not resolving. And dead letters, for the most part, they're good for knowledge, for knowing, you know, what's happening. But like I said, most of the time it's because there's a bug or the data is just bad. So to dead letter, then have to play in dead letters out of order, it's just a lot of overhead and work, and it doesn't get you anywhere, because you're better off just fixing the problem. Oh yeah, I want to say one thing also here. What was it? You know what? Never mind. Anyways, come to me at the end. Kafka and Zookeeper configuration. You can configure Kafka to be either consistent with partition, network partition, what do you call that? Handle network partitions, or it can be available and handle network partitions. You can pick one of the two, depending on the data you're using, you're collecting. When you create your topic, over provision, so more partitions than you think you'll need. Like I said, if you add partitions later, your ordering gets messed up for a while. Every new consumer, until all the old partitions expire out, all the old partition data expires out, will see things out of order. So just make sure you're thinking about scaling up when you do that. You know, don't go nuts. Don't put 1,000 partitions in there. That won't get you what you want. And finally, make sure to monitor it. Everything needs to be monitored, and this should just be like, duh, right? Quoting my 9-year-old. Consumer leg monitoring is really important. Broker monitoring, especially with under-replicated partitions and finding network partitions, so dual-headedness. Zookeeper, for the most part, it's just logs. But for the consumer leg, there's a tool called Burrow that can help out with that. So you don't get as many false positives as if you just watch JMX metrics off the consumer. And then finally, any questions? All right, no questions. I just wanted to say I was going to talk about difference between old brokers, commonly used brokers, and Kafka. One reason Kafka was developed also was that most brokers, such as your ActiveMQ, Apollo, RabbitMQ, are really great when they're in memory. But the moment things get persisted to the disk and back up, they're awful. They fall over, die, get slow. Consumers can't catch up. Kafka doesn't have that problem because it always puts it to disk. So that's one major difference. Yeah. No, it's not. You can set how often you want to flush the disk, but really it's going to be in that page cache on the OS, and the OS will flush it down, and it also you can set how often it forces the flush. Sync to the replica. So the sync to the replica depends on the producer AX. So if you say AX 0, then no. If you say AX 1, no. AX all, yeah. All right, though.